And then after that, we're on to curvilinear coordinates. So let's start with just this, like a nice, easy warm up. Any guesses before we get to actually calculating it?
I'm going to guess no, just because.
Yeah.
Yeah, at this point, you probably can smell some of these curly functions because you've got some X's and Y's permuted. Yep. So what would you guys do to prove it or just prove it? You guys 2 minutes, I guess. Probably reasonable for this. So what is it that I need to do to show that this is a non-conservative function or force field?
If it was conservative, then the curl would equal 0.
Yes, everywhere. So not just at maybe one special point. So one way or another, nice differential calculus thing to do. So through Stokes' theorem, this is equivalent to saying that any line integral you choose, any closed contour, would have a vanishing integral. So this is the integrand of the other side of Stokes' theorem, and it's much easier to use. And we're now able to use this notation because we said so. So this is d by dx, d by dy, and d by dz. Okay, we've got x component 2y, y component minus x, and then z component z. And then what'd you guys get for that? You get 0 for that, d by dy of z minus d by dz of negative x. Next I have a derivative with respect to x of z, and then a derivative with respect to z of 2y, so that's 0. And then finally, for k, I have -1, -2, -3. So it doesn't vanish, it's not particularly difficult, but this is definitely a non-conservative function. Which means the integral along a contour of a dot dl matters. So we really care about the details of whatever C1 is. Okay, so next question is it worth expanding this into one of those Stokes theorem type problems? Because, you know, maybe more practice with that is better. Okay, I'm gonna put my thumb on the scale and say yes too, because the more you see of this, and this one you have choices about, for instance, what sort of coordinates you might use. So I'll just leave it open. And this is actually the type of problem that you would see like in a textbook, where a lot of the details of how you would actually do this calculation is up to you. So I'll just say calculate, and then I'll draw the integral thingy on the surface. So we want to calculate integral sigma, that's a sigma. This surface integral of the curl of A on the surface. So this happens more and more, is that instead of writing all this stuff over and over and putting it downstairs at the bottom of that integral symbol, we'll just kind of the way that you would do, if you were writing code, is you just give the thing a name and refer to that name. So the surface itself, its name is sigma, just because, saves us some writing, a lot of writing. But it is the surface defined by x squared plus y squared plus z squared equals 1, and z is greater than or equal to 0. So in words, can somebody describe that surface for me?
That's half of a sphere.
Yeah, the unit sphere in the upper half plane. So as best as I can draw it, it might look something like this. So that is sigma. Okay. And that's all you got. So there are two ways of potentially doing this. You guys have already calculated the curl directly. So you know what you'd be getting into is an integrand if you were to use this directly. The other way of doing it, of course, is to appeal to Stokes' theorem and see if you want to parameterize the boundary of that surface. So I'll give you guys a couple of minutes. Pick whichever way seems easiest to do this, or not easiest if you're feeling like, challenged. Okay. How many people did the surface integral or started it? So the surface integral, I think, is easier math. There's just writing down the dot product in between the surface elements. So this last part, I think if anything's gonna get you, it's gonna be that. But we have the integrand, we have that it's just 3 in the k-hat direction. So I can write down this integral over the surface sigma of 0, 0, minus 3. We've already taken the curl. And then just as kind of a stand-in to start simplifying as much as possible, maybe you already know that some of these might have certain properties or vanish, but I'm just going to write this. Is it maybe the surface differential element has an x or a y or a z component? And I think it might, because if I take some spot like right here, it would point up, so that means z, and then I could put that in the xy plane. So I can't just generically say, actually, any of those vanish. But after I take the dot product, what I get is something that's actually like really nice. So I get 3 dz, d sigma z. And honestly, even the 3 can come out. So I get something that looks like this. And if nothing else, this looks like really nice, right? All I got to do is figure out generically what the z component of this little bit of differential area is. Okay, before doing that, I will point out that you could be done right now. So this has the geometric meaning of, so remember what dot products mean? It's like you're looking down. So for instance, if I just take the dot product of 2 vectors A and B, what is the geometric meaning of A dot B?
How much of A lies along B?
Yeah, so it's basically up to their own individual lengths. It's the shadow that A casts on B, right? So in a sense, what this is because we're just picking out the Z component, it's kind of like the shadow of the entire area if you're looking down the Z axis. So it turns out that this is really just the area projecting or looking down Z axis. And if you look at this surface down the Z axis, what does it look like?
It's a circle.
Yeah, it's just a unit circle. So it's just got area pi r squared, pi 1 squared, pi. So cheap argument is that this is going to be equal to pi. But that's, it's a little bit shady. I don't feel 100% comfortable with that. So let's go through the mechanics of actually showing that that's true. but that is what the geometric meaning of this is. It's like the projection that this entire surface would cast down if you're looking down the z-axis from this dot product. So I really hope we get pi. Okay, so what is sigma d sigma in general? Or can you just tell me what it is for spherical polar coordinates? And then we'll have to turn spherical polar coordinates into Cartesian coordinates with an appropriate sine or cosine. Okay, there are two parts of this, right? There's the actual area, and then there's where it points. And the where it points we'll kind of leave because maybe we don't need a full answer. We just need to know how much of it points in the z direction. Do I have any area component that includes like a dr? Does my plaquette of area extend farther out in the radial direction? I will just amuse myself drawing little plaquettes everywhere until somebody, if nothing else, guesses this yes or no question. So the question is should dr be in there anywhere? Which is to say, do any of these plaquettes extend in the radial direction?
Yeah.
I think they do, yeah, because it's a closed surface, right?
So the surface is open on the bottom. Otherwise, we would
Okay.
have 0 because there's no line integrals. Yeah, so it's like basically a hemispherical bowl turned upside down. So one way of thinking about it is if you look at our definition of the surface itself, what is x squared plus y squared plus z squared?
One.
Yes. What is it in radial coordinates?
R squared.
R squared. So R squared is 1 is another way of specifying the surface. So the surface is a surface of constant R, so we should not have any dr in this. The other way of thinking about it is if you look at any of these individual plaquettes, which at this point I've maybe drawn too many of, they go a little bit in the d phi direction in the xy plane, and then they go a little bit in the d theta direction. They come down as in latitude and longitude. But if you're walking around the surface of Earth and you're measuring areas on the surface of Earth, you'll change latitude and longitude, but if Earth was perfectly spherical, you wouldn't change radius. So this thing has d thetas and d phis, but it does not have any drs because we're on a surface of constant r. Or the other way of thinking about it is directly looking at one of these plaquettes and realizing, oh, I'm moving in theta direction, I'm moving in phi direction, but I'm always at r equals 1. Okay, the problem is the units of this are currently wrong. What do I need to put in front of this, the scale factor, to get the units right?
R squared sine theta.
Yes, r squared sine theta. So we get an r sine theta from the d phi part. So this is r sine theta. D phi will give us a little bit of actual distance, and then the d theta times r will give us a little bit of actual distance. So at this point, probably hopefully you're comfortable with just saying like scale factors. And in fact, what's true about r squared on this surface? So again, r squared equals 1. So we can just say sine theta, d phi. Okay, so we made a lot of really good progress, and I've cluttered my drawing to the point of regretting it, but what part of this do we care about? We just need the z component. So what is the z component of this? The part that points upwards. Nothing fancy, just plain old ordinary trigonometry. we want to know the part of this that points in the z direction, and maybe just pick on this one. And we have theta that measures, it's technically called co-latitude. So from the z-axis instead of the equator. So I just want the z component. So which trig function should I pick?
Cosine.
Yeah, the cosine part. So overall, what we get is -3 integral over the surface. And then we'll have to specify what that surface is. And then we have r squared, but r is 1, sine theta. Then we get a cosine theta because we're picking the z component, d theta, d phi. Okay, so now specify the surface. What do I have to integrate over in the phi direction? The phi limits of integration.
Zero to 2 pi.
0 to pi over 2.
So all the way around in the phi direction, the entire trip around the equator. And then, okay, for this hemispherical surface, what do I have to integrate over for the theta direction? Which I think somebody said, thinking I said theta instead of phi first.
That was me, yeah.
So
0
that's,
to pi over 2.
yeah, exactly. So it's half of, so we got to go from the North Pole to the equator. Okay, and then sine theta, cos theta, d theta, d phi, and the -3 is still there. So that's the whole thing at this point. It's just kind of a calc 2 exercise. We get the 2 pi from the theta integral, and then sine cosine, we would get cosine squared or sine squared, however you want to do it. Or you could pack in that minus sign if you want. But after all of that, what you end up getting is -3 pi. Okay, so there's a little bit of dot, dot, dot there where we just, you know, the second integral we didn't go through the details of. Okay, easy part is the actual mechanics of the calculus. The hard part, and this is always probably going to be true, is the setting up of the integral itself. Like, wait a minute, what is d theta z, d sigma z, for instance? So any questions about that? Just for practice, I want to do the line integral method as well. Did anybody do the line integral thinking they were gonna? Line integrals are always easier, to be honest, I think. Maybe that's true. I'm sure somebody could come up with something. You did?
I did the line integral, yeah.
Did you get all the way to the end? I didn't
No,
give you
I
guys a
was
lot
just
of time.
finishing it up now.
Okay.
It did take longer than I thought it would.
Yeah, you got to come up with the parameterization like the other one. But yeah, let's do that. So you could also do method 2 and do a line integral. Try to clean up as much of this stuff as I can. Method 2, line integral. And of course, the first thing that you do before embarking on that is you say, the reason I'm able to do this is Stokes' theorem, where the integral over some surface of the curl of a vector function is equal to the closed line integral around the boundary a dot dl. And just symbolically, and you understand why this might be easier once, maybe even it sounded like natural for me, like, oh yeah, it's just d sigma z and the projection down to the plane. Like, no, I have to think about this stuff for a couple of minutes myself. So this really isn't obvious. So the reason to maybe do a line integral is like, line integral looks easier, symbols, everything, coming up with the element, line element too. So Stokes' theorem says we can do this, so we can do that. So that is step 0, justifying, evaluating this thing by using the line integral. Okay, what is the contour, the closed contour that we're going to take the line integral over?
I did the circle on the z plane, or the xy plane then, yeah.
So it's got to be if you visualize these surfaces as like drinking vessels or bubbles, soap bubbles, it's always got to be the boundary. It's always got to be the lip of the vessel, right? So in this case, you don't get to choose, like you choose a Gaussian surface. It's always the edge of the surface. Okay. So this has got to be, we'll call it the unit circle in the XY plane. Just to be a bit verbose about it. And that is a closed line integral. Okay, A itself is 2y minus xz. And we're going to dot that with, okay, maybe we can skip a step that we didn't skip at first in the surface integral. Generically, I have a d line element that's like dx, dy, dz. Can you argue any of those are 0 for this particular
dz is
contour?
definitely 0.
dz is 0. You're not coming up or down out of along the z-axis. So this is just dx, dy, 0. All right. And the reason to do that kind of early on in the calculation is that if I have a 0 element and I take a dot product, it kind of, saves me a little bit of work. So then I can dot stuff out and I get something that looks like this. 2y dx minus x dy along that same unit circle. And we've been here before, right? So this isn't so bad. So now I actually have to choose a parameterization. It's not like x or y is constant. I think we did a pretty straightforward example with this. What do you want to choose as a parameterization of this path around the xy plane unit circle?
Probably a pretty easy one is x equals cosine t, y equals sine t from t equals 0 to t equals 2 pi.
I like it. So x is unit circle, so it's just cosine of t. Y is sine of t, right? So basically starting at the positive x-axis and walking around the circle, and then t goes in between 0 and 2 pi. Which means that dx is minus sine t dt, and dy is equal to cosine t dt. That's it, just plug everything in. So now our line integral, which should be just one integral because it's a 1D curve, 1D surface is a curve. So 0 to 2 pi, we go all the way around to, consulting my dictionary, y is sine of t, dx, consulting my dictionary, dx is minus sine t dt, x is cosine of t, and then dy is cosine of t dt. Okay, you can factor out the dt's, you can collect some terms. There are probably a few ways of doing this. I think just immediately to me, using the fact that cosine squared plus sine squared equals 1, I guess you could express it like this, which is, if you really want to flex your ability to do trig identities, you could use, I guess, the double angle formula in reverse. And I think sine squared of t is 1 minus cosine of 2t over 2. But Wolfram alpha is fine at this point, and you should get, oh, I hope you really should get the same thing. You should get minus 3 pi. So the minus 3 from the function itself, and then the pi is, again, the geometric contribution. But should be the same thing. Okay, any questions about that? Okay, this is kind of how these quizzes will work out, and like always, I'm happy to take feedback. I like giving you guys hard problems and then assigning a lot of partial credit, because at the very least it evaluates the ability to do stuff that you might see in like a research or, you know, grad school setting. And I'll repeat this before the quiz, is if you see something like this, just like keep going, and it's okay if you don't get a final answer. Really in this class, I want to see like kind of technique and method.